In this video, I'm going to show the image of why we need a DAC-based TX driver in the SerDes system. Before showing the TX driver circuit image, we should look at the domain images, such as remote learning, office, social media, AI, cloud computing, data streaming, online business shopping, delivery system, self-driving, etc. Therefore, higher throughput demand comes from the areas of the data center, storage, automotive, high-definition video, media, e-commerce, high-performance computing, HPC, 5G wireless, IoT, etc. If we must go to a higher throughput, think about the change images for 5 seconds. Correct. The change of a higher throughput would be a higher speed. Furthermore, what are the change images of a higher data rate? First, the channel loss image shows you a higher data rate or frequency leads to a higher channel loss. Second, the on-chip device process spread or variation would be greater at a high frequency, since the operating frequency could be close to the device limits. Last, higher frequency operation will lead to a more aging concerns and a shorter lifetime of the SerDes because of its electron migration and self-heating inside the device and metal routings. Since the higher data rate will lead to so many degradation or concern, how could we double the throughput but keep the same speed? Think about your data modulation image or encoding images for 5 seconds. Bingo! As we discussed in the Why Painful video, if every 2 bits NRZ data is encoded into a 4 voltage level painful data stream, then the data bandwidth is the same. The data transmission image shows you the maximum transmission of both NRZ and painful signals is the same, which is 1 UI. But the throughput images show you there are 8 bits of NRZ data in the channel, while there are 16 bits of painful data in the channel. Obviously, the transmission image shows you that the painful can double the data throughput, but keep the data bandwidth without upgrading the infrastructure like the cable under the same channel loss as the NRZ at half throughput. Let's pause a bit. Do you see any TX driver requirements for the data modulation images? Great. The TX must support different data modulation for either high throughput or traditional low throughput transmission as a multi-protocol SerDes. The digital to analog converter DAC-based transmitter are suitable for providing different modulation formats. For example, NRZ, PAN4, PAN8, OVDM, etc. easily. Although the data transmission can mitigate the speed issue, can we keep double the throughput by pushing the PAN4 to PAN8? Of course not. As we discussed in the Why NRZ video, the PAN4 has lots of design overhead than the NRZ. If we even push further to PAN8, the design change will be tremendous at such high data rate and low price SerDes. Therefore, people may keep pushing the baud rate of the PAN4 higher. Any issue with that? Correct. You should be very familiar with the channel loss image. A higher data rate leads to a higher channel loss. From our several equalization videos, the equalization image shows you that the more complicated equation would be effective in dealing with a higher channel loss greater than 30 dB at the next rate. Think about the TX FFE equalization images for 5 seconds. Correct. To equalize the intersymbol interference ISI precisely, more numbers FFE taps would help. However, the more FFE taps in the traditional analog-based approach, the design overhead in power, area, and speed is big. Fortunately, with the DSP bits of help, the equalizer supports long FFE filters without overhead to the TX clocking or loading, since equalization is done in the digital domain, not the analog domain. So, in the DAC-based TX, the FFE tap generation and coefficient multiplication are performed in the DSP, and the DAC simply serializes the data to convert it into a linear analog voltage at the TX output. In addition to the ISI equalization, what else do we need more FFE taps? Think about your impedance matching for 5 seconds. Right, reflection. A very high data rate painful SerDes would be very sensitive to any impedance mismatch or reflection, even at a very good free-chip BGA package. Therefore, the reflection cancellation can be applied either at the TX FFE or RX-DFE. However, the traditional 3-tap FFE in the analog domain were not enough to cover the round trip of a reflection in the package dimension. Therefore, 8-tap FFE could be a realistic number to either mitigate the ISI or the reflection without much power overhead. Again, to implement the 8-tap FFE, the DAC-based TX easily supports the long FFE filter without overhead in the digital domain, and that's the reason the DAC-based TX is very powerful. Here are the summarized images of why we need a DAC-based TX driver in the SerDes system. Due to a higher throughput demand, a more complicated data modulation scheme is needed to keep the same baud rate and reuse the infrastructures. In addition to advanced data modulation, the multi-protocol SerDes need to be back compatible with the other NRZ protocols. Therefore, the DAC-based transmitters are easy to provide different modulation formats with much less overhead than the analog-based TX. Next, we might keep increasing the SerDes baud rate, but both the ISI and reflection issue must be mitigated through the complicated TX FFE. Unfortunately, the design overhead of a complicated TX FFE in the analog-based TX would lead to lots of power, area, and speed overhead, which was the main reason the number of taps was limited to 4 or less. As we discussed in the why analog-based TX video, that's the fundamental trade-off between the FFE flexibility and its output self-loading. Even though we've discussed the DAC-based TX could have lots of power overhead at the digital gates operating at a very high speed, the DAC-based TX can easily implement several taps greater than 5 easy because the very complicated equalization is performed in the digital signal processing DSP. Indeed, the DAC-based TX did consume lots of digital power in the DSP or FIR with the old process node, but the power will scale well with the advanced technology. With proper design, we do see the power overhead of the digital gates in the DAC-based TX indeed reduce a bit in 7nm or 5nm FinFET technology. Therefore, the digital power will not be a big concern in the DAC-based TX anymore. Lastly, the DAC-based transmitter provides flexibility to cover the arbitrary number of taps and different modulation schemes in most advanced SerDes technology without any self-loading trade-off that analog-based TX would have, and the power overhead is minimized as well. The DAC-based TX become much more popular in very high-speed SerDes with very advanced technology. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.